today I'll be talking about WarpStream. And so the talk's called Beyond Tiered Storage, Deep Dive into WarpStream Storage Engine. And so if you're not familiar, WarpStream is a kind of Kafka protocol compatible distributed system. It has a really unique deployment model we call BYOC, where kind of we run a stateless data plane in the customer's cloud account, and we run a control plane remotely. And what I'm going to focus on today a little bit is how kind of the completely stateless architecture, how it works, how the storage engine works, and how it's a little bit different than tiered storage and things like open source Kafka. So usually the way I like to start off by explaining this is, and there'll be plenty of time for questions at the end, by the way. But usually the way I like to start off explaining this is, why tiered storage in the first place? And the main reason that's pretty obvious, right? Like, disks are really expensive, especially in the cloud. If you're storing data for a long time, and a long time can even be just like a couple days or even a week at higher volumes, you can easily end up with like 80% of the cost of your cluster being, local SSDs, EBS volumes. The math for this is pretty straightforward, right? If you look at something like GP2 in AWS, they cost about 10 cents per gigabyte. And that's pre-replication, right? If your Kafka cluster is triply replicated, you're looking more like 30 cents per gigabyte. And then you probably don't run your clusters at 100% disk utilization. So once you add, 40 to 50% spare headroom, you're looking more like, 50 cents per gigabyte. In S3, you can store everything, 2 cents per gigabyte, replications included, and you don't have to over-provision, right? So as much as possible, you're dealing with kind of large volumes of data. You want to get it into object storage to keep it cost-effective. There's a lot of ways you can play with these numbers, right? You can run Kafka with double replication instead of triple replication. You can use local SSDs instead of EBS. But there's kind of like no escaping the gravity of this math. If you want to retain a lot of data and you want it to be cost effective in a cloud environment, it kind of has to eventually make its way to object storage. So that's why tiered storage was added to systems like Kafka, and a lot of other distributed systems do it as well. And it definitely does help if you're just, trying to retain data for 7 days for like an emergency. Tiered storage can help. But there's a lot of stuff that comes, it doesn't kind of solve all of the problems, I think, with like kind of reducing your costs in cloud environments. And so the approach we took with WarpStream was to get rid of all the disks entirely. So if you think about a typical Apache Kafka cluster, we have these really stateful brokers. They have attached storage that makes operations complex, right? You have to rebalance partitions. You add nodes, you remove nodes. All the partitions have to be moved. All the data has to be copied. If nodes are participating in KRAFT, you have to think about that. Topics have leaders. They can be under-replicated. All the kind of stuff you maybe are used to dealing with if you're running Kafka yourself. And just in general, balancing is always really hard. Kind of all of these things with running kind of, at least like kind of standard open source Kafka, it all kind of derives from the fact that the nodes are stateful, right? And so when we were designing WarpStream, one of the main motivations for getting rid of the disks entirely was to kind of simplify some of this operational stuff. The other reason that we really wanted to get rid of all the disks is to reduce networking costs. This is one of the things that people often don't realize about running Kafka in the cloud as well. But if you're running like a multi-AZ Kafka cluster and you have brokers and different availability zones, you're replicating data across availability zones a lot, right? If you think about the produce pass, 2/3 of the time your producer is going to be running in a different zone than the topic partition leader for the partition it's producing to. And then once the data reaches the broker that's the leader for a given topic partition, it has to be copied to followers in 2 different availability zones. So that's a minimum of 5.3 cents per gigabyte run through the system. And that's if you have a perfectly configured Kafka cluster with fetch from follower enabled. If you don't have fetch from follower enabled, you can probably like double that number. 5.3 cents per gigabyte just to get it over the network in a couple milliseconds versus, you could store it for more than 2 months in S3 for the same amount of money. So this is just to give you an idea of how expensive interzone networking is. There are ways to work around this too. You can run in 2 zones instead of 3, or run your topics with 2x replication. You can also run your Kafka clusters triply replicated in a single availability zone, but if that doesn't work for your producers and consumers, that can be painful. So this is one of the really big drivers of costs. And so this problem is also actually ultimately caused by the fact that the nodes are stateful because there are specific brokers that have to handle writes, and reads can also only be served by a specific replica set. And so that was one of the other motivating reasons for designing a system that was Kafka compatible but had no disks, which was to eliminate that problem. And so, we thought zero disk would be better. And so we built a system called WarpStream. You can think of it, it's meant to be a drop-in replacement for Apache Kafka. And the way it works is that instead of Kafka brokers, we have these things called agents that are these red boxes over here. The agents are completely stateless. They have no local disks, no topic partition leaders, no agent is special. Any agent can handle writes or reads for any topic partition. And that enables a lot of kind of interesting stuff. The first thing is that the kind of EBS volume cost issue I was talking about just disappears. The agents write directly to and from object storage. They don't need any local EBS volumes. And the interzone networking problem also goes away since any agent can write or read data for any topic partition. The producers produce to agents running in the same zone as them, and consumers always talk to agents running in the same zone as well. And the way this kind of works is the storage engine itself is built directly around the object store. So you don't deal with any manual replication between availability zones, and there's no buffering on the agents themselves. And then the way we provide the abstraction of Kafka is if you walk through the write path really quickly. Well, actually, that's the next thing I'm going to do, so I won't dig into that yet. But you can imagine a producer writes a batch of data to an agent. The agent buffers it for a little while. It's batching produce requests from hundreds of different clients for thousands of different topic partitions. And then every 250 milliseconds, it creates one file in the object store. That file contains batches of data for hundreds of clients, thousands of partitions. And then it goes to the control plane or the metadata store, which is the part that runs in our cloud. And I'll get into the details of this whole flow in the next few slides. But says like, hey, this file exists. And only once a file has been flushed to the object store and committed to the metadata store do we acknowledge it back to the producer. So you get the same kind of durability guarantees as AX equals all, but you have a higher latency. And I'll talk about the latency in a little bit. So how does this work? Right before I jump into that, I want to go over a couple numbers to explain how much things cost when you're interacting with object storage, because all of the storage engine design kind of falls out of these numbers. And so the thing to know about using object storage in the cloud, right, is that you pay for every I/O. Every put request costs money. Every get request costs money. Storage is very cheap, and networking is free. So you don't pay for any networking between your VMs and object storage. And these numbers look really small, 0.00, how many zeros that is for puts. And gets are like 1/10 the cost. But those numbers add up really quickly, right? You do those thousands of times per second, it gets big quick. And so everything about the storage engine is designed around minimizing the number of puts and gets. And anytime I can do more networking or trade storage amplification to reduce those two numbers, that's probably a good trade-off. Because, again, networking is free and storage is really cheap. So, most of you are probably really familiar with Kafka, right? You have brokers. The broker is responsible for specific topic partitions. On disk, that broker will have, a bunch of segment files, basically. It'll have one open segment file for every topic partition that it's the leader for. And the replicas will too. And then as new writes are coming in, batches are just getting append to the end of all the segment files. This works great, actually, on top of SSDs. It actually even works pretty decently on spinning disks, as long as you don't like f-sync. All the partitions, like you delay f-syncs, this will work pretty well. But this would be a disaster in terms of object storage. It would work if you had like 20 or 30 partitions or something. But once you get into the hundreds or thousands or tens of thousands of topic partitions, like I know some of you here have, it gets pretty expensive. It just wouldn't be cost effective. It would be even way more expensive than using interzone networking. And so the kind of like cardinal rule of WarpStream storage engine is that the relationship between the number of IOs against the object store must not be linear with the number of topic partitions in the system. It needs to be linear with the throughput of the system, but not the number of topic partitions. So how do you do that? Well, it's not that complicated, right? We just can't have files per topic partition. So what WarpStream has, the storage engine, it's basically an LSM, pretending to be Kafka. So what we do is we emit these files that contain data from many different topic partitions. And so, even if you have 1,000 topic partitions, you're only paying, every agent only has to make one file like every 250 milliseconds. So that works pretty well, but it creates a lot of problems that have to be solved. And the main problem here that's introduced is, if you think about Kafka, you're like, okay, I want to go read partition 6 for topic foo, and I want to start at offset 2000, right? Your client knows that some broker is the leader, one of the replicas for that topic partition. So you just go to that broker and you're like, hey, I want to start reading at offset 1000. There's a bunch of little skip indexes for the files, and the broker can just essentially, it has like 100 log segments or something, and it knows that the minimum and maximum for each log segment, and it can just basically jump to the right file, do a little bit of seeking, and it's pretty much, it knows where it is. And like the ordering of the partition, the batches themselves, it's encoded in the file, right? Because the file is in order. It's a log file. Once you do this, you have a much trickier problem, right? There's no node that owns this file. Any node can read this file. And when someone says, I want to read partition 2, topic B, starting at that batch, something needs to know which file that lives in and in order to read the batches. And so that's kind of the fundamental problem that we kind of have to solve. And so if we walk through the right path now, in a little bit more detail. So you have a client, it's running a standard Apache Kafka client, buffers and compresses some data, creates some batches, produces to an agent. That's the thing in the middle. The agent buffers again, right? Because it has hundreds of clients connected to it that are, sending batches for thousands of different topic partitions. Once that timer hits, or we have 4 or 8 megabytes of data in memory, the agent just writes a file to the object store. Now, interestingly, once the data is written to the object store, we still don't know the order, right? So you're like, I put some batches in the object store, but I don't know what the offsets are yet, and they're not determined yet. So once that file is written to the object store, we then go commit to the metadata store the fact that that file exists, and it's not until that step happens that that data actually exists in the system. And only once both of those operations have happened do we acknowledge the produce request back to the client. And that's why I mean it's ACKS equals all. If either flushing or committing fails, the client gets an error and the data is not persisted, right? And so I was talking a little bit earlier, right, about like, when you write to Kafka, all your batches get logically sequenced by the leader. That's basically what the leader's job is, right? The broker, the leader for a topic partition, its job is to order the batches. So one of the primary jobs. And in WarpStream, there's no leaders. And what happens all the time is you have 2 agents that are flushing batches of data concurrently for the same partition. And you need to eventually decide on a final order. And so the way that this works is, so in Kafka, the broker is the sequencer for a topic partition. In WarpStream, the control plane / metadata store is a sequencer for the entire cluster. And so when you commit the file, only then are offsets assigned, and we can return them back to the client. And the reason we're able to scale it this way is because with Kafka, the topic partition leader has to handle all of the raw data and then do all the sequencing. With WarpStream, the metadata store only has to sequence like the offsets, basically, right? It doesn't receive any of the raw data. And so you can scale that to millions and millions of operations per second, tens of gigabytes per second, and that's still a tractable problem because you're not actually processing the raw data. Okay, next problem. So none of the agents are topic partition leaders. That's going to make reads really inefficient if you do it naively, right? If every time a consumer came in and wanted to fetch some data, we just did a GET request against the object store, well, when you have hundreds or thousands of clients reading from hundreds or thousands of topic partitions, you're going to be spending millions of dollars on S3 GET requests. It just wouldn't work. And so what we do is, if you're familiar with Kafka, the way that Kafka makes this work is like, it's very rare that a Kafka consumer actually reads from the disk, right? What happens is you write to a Kafka broker, the leader, sequences that data, writes it to disk. Part of writing it to disk is the data gets written through the operating system page cache, right? And then the followers do the same thing. And then when a consumer comes in, and most of the time, hopefully your consumers are caught up, they want to read that same data, they go to the Kafka will go to the operating system, it'll do the send file syscall, and the operating system will be like, I'm not even going to go talk to the disk, I already have that block of data in the page cache. And so most of the time, like, you can, like a well-tuned Kafka cluster, you can go look at the disk stats and you might be writing a lot, but the read throughput off the disk might be really low because everything's just, it's essentially replicated in durable memory, right? And so we need to reintroduce something like that, but in a more distributed setting with no leaders. And so the solution we came up with is this thing, I like to call it distributed mmap. It's not that crazy or novel, it's basically a consistent hashing ring. But the way the implementation details are a little bit interesting. And so in this diagram, what I have is 3 different consumers. There's a blue consumer, an orange consumer, and a green consumer. They're each reading different topic partitions. And the requests come in, and they're reading completely different size chunks of data, right? And those requests come into the agents. And the agents know what other agents are running in the same availability zone as them, and they just make a consistent hashing ring, right? Like a distributed KV store or something. And what they do is when you're, as part of the read path, the agents consult the metadata store, and they're like, okay, I need to go read this range of bytes from this file. And they take that, the file ID and the range of bytes they want to read, they run that through the hashing algorithm, and it'll be like, oh, that range of bytes is owned by agent 2. So even though these 3 consumers hit 3 different agents, since they're reading kind of adjacent data in the object store, the fetch request will kind of get funneled via sub requests to the agent in the middle. The agent in the middle will receive these requests with a variety of different timings, right? It could receive all 3 more or less concurrently. There could be some delay between them. But ultimately what it'll know is that okay, people are asking for data that is contained in this kind of 4 megabyte block. And so what it'll do is it'll duplicate all of those fetch requests, and it'll make a single GET request to the object store to load exactly 4 megabytes of data. So even if you only ask for 16 kilobytes, it might do a bit of an overread. It'll grab that 4 megabytes of data, chop it up into tiny little pieces, throw that into an in-memory cache, and then it will serve all of the sub-requests out of that in-memory cache. It's kind of hard to visualize this, but what effectively this does is that no matter how many partitions you have or how many consumers you have, if they're all caught up, basically, or caught up to within the last let's say 20 to 30 seconds, however big your cache is, you will make exactly 1 GET request for every 4 megabytes of data that's written through the system in every availability zone. And if you do the math on that, that's extremely cost effective. You can do that all day. And so that's how we serve the live reads. And this ends up scaling really well. And part of the reason this works is that the most recent data is limited to the most recent set of files, so that this cache is very, very, very effective. But that only works for live reads, right? One of your consumers ultimately is going to end up lagging, or one day you're going to have to replay a bunch of data from the beginning of time or whatever it is. You're going to want to read some historical data. And so if you take this entire diagram here, I've condensed it into that little graph on the right where you have an agent and then 3 consumers reading from it. And so the live consumers are all sharing IOs, right? They're all reading kind of the most recent data, the newest files. It's all cache hits, everything's gravy. Consumer 4, though, is reading some old data, and there's no opportunity for it to share IO. And so you can imagine, if you have a large cluster of agents, let's say you got 20 agents, they're each making files 4 times per second. That's 80 files per second. You let that run for days or weeks, you're going to end up with a lot of small files, and historical reads will just be insanely expensive. And so the way we solve this problem is basically the same way everyone solves the small file problem in the kind of LSM world, is we just run compactions, right? So there's this background process running in the agents. We essentially scan for small files that were written, and we just compact them together into one big file. And so when you do that, maybe in the files emitted by the agents in a given file, you only have 32 or 64 kilobytes of data for a given partition. But once you combine files and do these compactions, eventually you get megabytes of data for a given partition within a single file. And that means when this historical consumer comes in and it wants to read partition 2 of topic X from start to finish, every time it makes a GET request, it can load 4 megabytes of data, and it's all relevant, right? And so that's how we make the historical reads really cost effective as well. So just to give you an idea of like how expensive some of the stuff I'm talking about is, if you run a self-hosted kind of open source Apache Kafka cluster with replication factor 3 and you run it in 3 availability zones, the hardware cost is almost a rounding error. The cost, this is with fetch from follower enabled, by the way, for a 1 gigabyte per second workload, just on interzone networking, you'll end up spending like $1.68 million per year without any discounts. And on, this is an older slide. Usually I show the EBS cost here, and it's like $500,000 or whatever, but I guess you don't even need to show it because the networking is so high. Whereas with WarpStream, pretend you need the same number of agents as you need brokers. Networking is almost free. And yes, we do introduce these object storage API fees, but because everything was designed around the minimizing number of puts and guests, the amount of money you pay for object storage is like less than 1/10 of just what you would spend on networking, let alone EBS. Now, this obviously changes. If you're a really big company, like you can get pretty decent discounts on interzone networking, and it may not be this extreme, but it's almost always more cost effective to do things this way. And again, there's just this kind of trade-off around latency. And so I talked about latency a bunch. Like, what do I mean by that? WarpStream is still very much real time. Kind of expect P99 producer to consumer latency to be around 1 second, maybe a little less. And then the P99 producer latency is usually about 400 milliseconds, maybe 500 milliseconds with the default configuration. You might have heard about this, but like a lot of the cloud providers now are starting to offer kind of lower latency versions of their object stores. Azure's had this for a long time. Amazon recently introduced it with its S3 Express 1 zone. GCP doesn't have anything yet, but I bet they will soon. And using S3 Express 1 zone, it's actually really interesting. So S3 Express 1, it's in the name. Your data is only available in a single zone, but it's really low latency. And so what you can do with WarpStream, if you're willing to pay more money but you want to keep the architecture, is you can set up 3 S3 Express 1 zone buckets, and then we'll write all your data to a quorum of 3 buckets. And so you get still the kind of high availability, high durability, but with much lower latency at the expense of cost. And if you run it in that mode, you can get the P99 producer latency under 150 milliseconds. I think actually I had someone benchmarking this recently, and they got it under 100, but let's say under 150. And the other trade-off that you tend to have to pay with these kind of lower latency object stores is the storage costs are way higher. Like, so you pay more for like the amount of data that you're writing, but you also pay for storage. But this is kind of where, I kind of started off this talk by, kind of saying tiered storage is not the best solution. And now I walk that back and say, with stuff like this, you can actually reintroduce the concept of tiered storage, but now you're not tiering between local disks and disaggregated storage. You're tiering between low latency, expensive disaggregated storage and high latency, cheap disaggregated storage. And so what we do with the WarpStream agents, if you're running it in low latency mode, is we land the data from your produce requests into S3 Express 1 zone, so you get that low produce latency. And then when we run the compactions, seconds or minutes later, the compaction reads from the S3 Express 1 zone buckets and then compacts the data into S3 standard. And so you don't end up paying high storage costs, you just pay the higher fee associated with writing large volumes of data into S3 Express 1 zone. And so that's like my trick. We actually do tiered storage, but just not with any low risks.